Hello everyone, welcome to Bite Size Coding. Today we are going to discuss about low latency and high frequency techniques. Okay, so today we are going to focus on one specific thing, that is the cache-aware design. So these are some of the techniques that are used for low latency and high frequency coding. So cache-aware design that we are going to discuss today. Kernel bypass. So kernel bypass is basically it eliminates the overheads of in-kernel network stacks by moving the protocol processing to user space. If lockless data structures and algorithms, so if you are using multi-threading and there are shared resources, so then yeah, in order for concurrency controls, many times you have to lock the shared resource. So that results in a performance hit. Memory allocation, every time you do a dynamic memory allocation, there's a performance hit. There are a lot of compiler optimizations that you can do. There is caching, multi-threading wherever it is possible. And then like in the critical path, typically we generally do not use any branching. So no if else, because whenever you do if else, let's say if there is a jump, then all the caches has to be wiped out. All the instructions which are prefetched, those might not be of use. Okay. So let's talk about cache-aware design. So basically, cache is an intermediate memory between CPU and main memory. By main memory, I mean RAM. Okay. And by cache-aware design, we refers it I mean that like it's a programming approach that takes into consideration the memory hierarchy and cache behavior of the underlying computer architecture. So the goal is to optimize the program performance by minimizing cache miss or and maximizing cache utilization. Okay. So so cache memory is basically the intermediate memory between CPU and the main memory. And the underlying principle behind cache memory is locality of reference. So what it means is if a data is accessed once, it is likely to be accessed again in the near future. So if such data is stored in the cache, it reduces significantly the time required to access it, and it will result in a notable improvement and of the overall performance. Okay. So when a CPU water cache hit or miss, so when a CPU needs to retrieve data, it initially checks the cache memory. So if the data is present in the cache, it is referred to as a cache hit. On the other hand, if the data is not found in the cache, it results in a cache miss. And in these scenarios, the CPU has to access the main memory to obtain the data. Okay. Now there's a limited size of the cache. So whenever there is a cache miss, it has to decide which data it has to discard. So there are some cache policies like least recently used, which discards the data that has remained unused for the longest duration. And then there is MRU, most recently used, which prioritizes the removal of the most recently accessed data. Now, if you see this pyramid, it's basically the different types of memory, those are available. So at the top is the CPU registers, which are the fastest but the smallest in the size. And at the bottom, you see the disk drive, which are the biggest, but they are the slowest in speed. Okay, so L1 cache is faster. So L1 is typically divided into two parts, one for storing the instruction cache and one for storing the data. And it is generally embedded directly into the CPU. L2 cache is slower in size. Sorry, not slower in size. It's slower in size comparatively to other caches, but it's larger in size compared to L1. And it can be shared among multiple cores or exclusive to a single core. Now, L3 cache. So L3 cache is also known as the last level cache. It is larger than both L1 and L2, but it's slower than them. It's generally located outside the CPU and is generally shared by all the cores. So how do you see like what type of L1 cache, L2 cache do you have. So if you are using a Windows box, you can go to Task Manager, and then you can go to the Performance tab, and at the right bottom you can see there is a L1 cache, L2 cache, L3 cache. So now one thing which I want to know, specify that L1 cache is 512 KB, but if you see the number of the cores are 8. Okay, so it's basically divided between the 8 cores. So it will be like 512 over 8, so it will be like around 64 KB, which is available to each core. Okay. Now, if you are using Unix or Linux on your Windows box using WSL, okay, so then there is another command. You can do get conf -a, and you can just grep for cache. So right now I'm running Ubuntu on my Windows box. So it's the same box. So if you see here, there is a level 1 I cache, which is basically the instruction cache size, which is 32 KB. Okay. And level 1 data cache size, which is again 32 KB. So, and you can see that cache association, there are 8. So basically it's 64 KB for the level 1 cache. And like if you add them together, it will be 512. Okay. So now we'll look at a small code to see how actually the cache like affects the program. Okay. And basically like we'll look at like a simple, we'll take a simple matrix. Okay. And we have to do a sum of all the elements. Okay. And in one case, we'll do a row wise traversal, row major traversal, and in one way we'll and in another approach we'll do a column traversal. Okay, so basically here is okay, so it's a very simple straightforward program. uh, there is a int 2D array which is declared. Okay, rows and columns which are of 2000 size each, and then we are initializing the array with some random values. Okay, so it's just going through each element and just assigning some random value. Now the auto start chrono high resolution clock, that is just to measure the time, that like how much time does it take to do the sum. So if you see here, it starts here, and then once we do all the sum, then it ends. So then, and finally we are printing how much time does it take, okay, for if you do a row major traversal. Okay, so what does it actually mean by row major traversal? That we are going to get all the elements for a row, add them together, okay, and then we'll go to the next row. Okay, so one thing is basically memory is linear, right? So in the sense that although it's a two-dimensional array, but the way the memory, it's represented in memory. So let's say, for example, you have a 3 cross 3 2D array. Okay, so there are 3 rows, 3 elements, 3 columns. So for the second row, the first element will be just after the last element of the first row. Okay, so if you linearly see, let's say an integer take like 4 bytes, 32 bits. Okay, and the starting address for storing a 3 cross 3 array is basically, so if the starting there's a 3 cross 3 array, and the starting memory space is 100. Int is taking 4 bytes. Okay, so first element will be at 100, second will be at 104, then 108. Okay, so it will keep on going like that. Okay, so it's going linear, right? So the first is at 100, the second one is at 104, the third one is at 108. The fourth element, which is now the second row, which is starting, is at 112. Okay, so it will work like that. Okay, so this is basically, so if you see here, we are running two loops for integer I is equal to I is less than rows, j is equal to 0, j is less than columns, and then we are doing a row wise sum. Okay, so that's the first program. Now if we do, okay, so this is exactly the same program. The only difference, so we are taking a similar like a 2D array with 2000 elements, and we are initializing the array with some random values. Okay, and then basically here we are just flipping the order of the two loops, right? So what is happening here is we are doing a column wise traversal. Okay, so when you're doing a row wise traversal, basically you're trying to access the memory which are next to each other, right? But when you're doing a column wise traversal, what will actually happen is like uh, you're taking the column from the first row, okay? Then you're taking the same column from the second row, okay? So you're taking a big jump from first row to second row, and it's not a linear accessing. You're not accessing the memory linearly. So you're not doing like 100, 104, 108. You're doing like 100, then let's say the next row starts at 200. The first column of the next row starts at 200. So you're jumping from 100, then 200. Okay. So if you do these type of memory access, right? So in that case, the data will not be present in the L1 cache, right? So it will be a cache miss. And then in that case, it has to go into the main memory, and it will take more cycles. It has to evict some data from the cache. It has to copy the data. So it will take more time. So theoretically speaking, this matrix underscore column.cpp should take more time to run it. Okay, so let's try to run both of them and see. Okay, so here if you see the row major traversal time, it took close to 0.009 seconds. Okay, now if we do the same for, so for a column major traversal time, if you see, it took like significantly more time, so 0.03 seconds. Now, there's a very good tool. It's called Valgrind. Like if you have done like C++ coding, you might have come across it, like uh, obviously. So basically, Valgrind is an instrumentation framework that provides like dynamic analysis of your program. So there are multiple Valgrind tools that can automatically detect memory management, threading bugs, and can profile your program in detail. Okay. So the way you run Valgrind. So one of the tools that Valgrind provides is called cache grind. So cache grind is a tool for doing cache simulation and annotating your source code with the number of cache misses. So it uses a simulation for the machine with a split L1 cache. So that is like an instruction in the data cache, and a unified L2 cache. Although there are different arguments which you can specify, like what is the size of your L1 memory, what is the size of L1 cache, what is the size of L2 cache. Okay. So the way to run it is Valgrind. You have to do -2 is equal to cache grind. Then you have to specify the binary. So first we'll run it on the row order traversal. Okay. Then, okay, so let's run it. Okay. So if you see its output, right, you see that the miss rate for the L1 cache data, okay, is 0.4%. Okay, these are the references, these are the reads, these are the writes. Okay, then these are the D1 misses, so around 520K. There are miss, and then this is the miss rate, which is the 0.4%. Okay, now let's try to run the similar thing, the same thing for the column. Okay, so if you see, there are significant more misses, like, so there are close to like 4 million misses, right? The miss rate is 2.9%. So the miss rate, so basically if you see, there are a lot more misses, and because of it, the column major traversal, it took more time. Okay, so you can play around with different options. There are like, so once you run valgrind, it will also create two files, right? So cache grind.out.pid. Okay, and so basically there is another tool which comes with valgrind. It's called cg_annotate. So the good thing about cg_annotate is, like, once you run it with your cache grind output, it can show you what the statistics at function level. Okay, so you can look at the cache grind, val grind, and these are like some of very powerful tools, and it can give you an idea about your coding style, like where there is more cache miss. Okay, and it can help you in optimizing your code. So that's all for this session. Okay, if you have any questions, put a comment. If you want more details about anything, I will I can make another video. And have a good day. Thank you.